this is your session. See, that was the first thing that got recorded right there, what I just said. So my idea, having finally gotten around to grading, which is to say looking through and making marks on homework, I'm concerned that maybe, or suspect, I don't know, people don't look at the homework after they've turned it in and after it's been graded and the posted solution nearly enough. And I don't think I talk about it enough. So I was thinking maybe, hey, maybe we could revisit those homework problems. Oh, what should I have done? What was wrong? Kind of gets me upset when like nobody gets some problems right. Like maybe almost like there's several people that get almost everything right, but there's not a single person to get everything right. I take that personally on me. Like, what did I do? So I don't know. That was my idea, but I will take suggestions. Just called it out. Kinds of problems. You could just ask what's going to be on the exam. Go ahead, get that out of the way. What's going to be on the exam? I haven't written the exam, so it's really difficult for me to tell you what's on the exam. I can't see.
How many questions do you plan to do?
I don't know. Somewhere 4 or more.
How long was she? 3?
Probably not 6. She gave 3 today? I bet they were harder than mine.
Well, there'd be a curve on this exam.
Wow, that's me looking into the future. Don't know. Don't know. I go like, so if you guys got together and you planned and you all bombed it together for unity, and you did it just to go like, holy crap, the highest grade was, pick a number, and I don't think I'd have much of a choice but to just say, we're having a hard time making eye contact, aren't we? Just joking. He keeps looking around you. But anyway, yeah, I don't know. I'm not anti-curve, but I would like to write an exam that didn't need to be curved. I would like to teach a course so well and write an exam so well that would never ever need to be curved. But I've heard many of my colleagues go, I don't curve. I'm like, all right, whatever.
Plenty of teachers who say they don't curve.
Yeah, I figured that too.
Also
Yeah.
curve.
Yeah. But
It's a classic.
anyway, I used to break the curve. I used to have professors that like what they would do is they'd only give a curve for the person that made the highest grade and make them up to 100. And I'd make 100. And my classmates would. This is getting recorded, so it's not good.
You gotta discount that. If someone gets 100.
You think no, it's not true. No. But I like people get 100 over 100. No, I don't mind that. Yeah, what again? They don't have an A plus in the grading scheme, so it doesn't really matter to me. I had one student without any curves made 107. Never got a single problem wrong. And sometimes on homework, like I would grade the homework, and I'm like, ha ha ha! I got you, Jack Breton. There, that's his name, Jack Breton. Shouldn't give that away. Doesn't matter. He's got a job at Bose. I got to tell you, kid was brilliant. But I offered some extra credit, and he took every extra credit opportunity. Yeah, just all the time. Yeah. But let's not talk about other people besides Jack Breton, who I'm a big fan of.
What's the most important topic?
What's the most important topic? Okay, most important topic. I will go through it. Let's take a look. Let's take a journey together. We did this a little bit in the last class where I went through each of the homework, but I would definitely say, from my recollection, that homeworks 1 through 3 aren't that important, because you already covered the really important stuff, and all of those really gets recovered in more depth in like everything from homework 4 on. And then homework 4, and this is a really important thing to me that I did notice, is that there's still people that are like, for a closed system, which is just a chunk of mass, and that's what homework 4 is about. They will still use enthalpy. Enthalpy really isn't used for stuff when you have a closed system. And I got to be careful when I'm saying a closed system, because sometimes what we will consider something where there's flow going on if we draw the box around it, right? So if there's no flow, like an inflow and an outflow or a circulating flow, we don't really use enthalpy for any of that. That's all about internal energy and about the energy, because you just think about this chunk. You got this chunk of stuff, and all the molecules are bouncing off of each other and getting excited. That's what internal energy is. We use internal energy for that. But when we're flowing, there isn't like this, it's just, there is internal energy, but there's something else. There's like this like flow energy that's the pressurized volume. So if you take a look, and did I put it in here? And if you want, I made some copies of this if you want to pass around that. I just took the border off of the thing if you want to pass around. That big equation thing, if you can give me one though. I made it look about it. Just one. Thank you. So this is what I'm referring to right here. In enthalpy, we have H is internal energy plus this PV term right here. And, you know, if it's, we don't really, we really just, that's just going to be a type of work that's taking place. Like we call it like flow work sometimes. So for a open system, you really don't, we go ahead and use enthalpy because it's internal energy plus this other thing that's taking place. Pressure times, often would be that change. But it's, you know, it's trying to put it into other terms beside what I've already repeated right there. So if we go back to, I actually put these up here for a reason. So let's see. Okay, so I'm going to jump to homework 5 actually. So homeworks 5 and 6. I tested on some of these on exam 2. And we could also go over exam 2 if you'd like. Might be a useful portion of our time. But these are all closed systems. You wouldn't use enthalpy for any of these. You'd use that first law, that closed system first law right there. So make that big enough right there. Internal energy, change in internal energy is going to equal to the heat that's being transferred minus the work out, right? So there's heat in and work out by definition in terms of their signs. And here's what the end state and the initial state, and that's true for all of these problems. And so when you recognize that, it's part of being the problem being this type of nature, you go through that. And then I just did a problem like here. I didn't have a single person approach this problem correctly in homework 9, I think. Maybe it was in homework 10. It was homework 9. We were doing it was homework 10 where we were doing the generation. Do you recognize what's special about this problem, about what happens here? That's got to be 2 stages. That this piston falls down. And because the piston's there, it's free and it weighs something. We don't know what it weighs. We don't care. We could set it up so we would have to find out how much it weighs, but we don't know. What it does is it causes a constant pressure because its weight is the same all the way as it's moving downwards, right? I mean, it could be that you were holding it and then you let go and then the thing starts rising up. But almost all these problems are that we were holding it and let it go and its weight causes it because it has the same force because the weight doesn't change and it's got the same area, so it's got to have the same pressure, right? I hopefully that, like, because there's been lots and lots of problems like that along the way, like the same one with what it looks like up here. But now it's got to stop, and so it comes down to right here. And it hits that, so it was constant pressure process till it gets there. And now, if something continues to happen to it, it's a constant volume process. So you got to do it in 2 stages, right? So that was something that was sort of like, wow, I thought we did enough of these that people would see them, but so. And when I'm writing an exam, I am not going, this will show them. I am like, I want to see if they're able to do this. Like, can they demonstrate their ability to solve a problem right here? And when people no one solved it yet, I want to say, hey, don't do that, and then measure it again, right? So if I was going to tell you, I haven't made a decision, but I'm telling you how my brain works. You don't really want to know, but yes.
I was just going to say, hypothetically speaking, could we see something like that?
Yeah, absolutely. I don't know for sure, but I'll put together probably a bunch of questions and at 11 or 12 o'clock tonight, having taken it and gone back and forth and argued with myself, and I'll decide. I'm not going to commit to it. I'm really good at last minute things, so yeah, I'm trying. Here's another this type of problem where we're putting work in, but it's rigid. It's a rigid tank. It's not one of these piston ones. That's a constant volume process, and therefore there's no work done. But there is, in this case, this is a special case because there's work being put in from the outside. You could also do that with an electric heater coil. You'd have the same effect. That external source of work that is not pressure and volume based. Yes, sir.
Will we have like a US units problem, or will it all be in SI?
You know, I probably won't because I don't need to make it that much more complicated. I use some US units because I wanted you to be exposed to it because it does exist in the world. So you wouldn't see it for the first time on your first day at work if you happen to work on a place that does thermo. And uses U.S. units, and it's all over the place. I mean, you will never get rid of it. And as much as anybody who says, I don't believe you, Dr. Dillon, you're an old man. You work from an old industry that's dying. It's not true. Ships aren't dying. Just American ships are dying. But yes, it's pervasive. It's everywhere. So no, but that's my reasoning for the U.S. units, but I won't try to mess with you too much because U.S. units, as I agree with you, they suck. No way around it. Problem like this, that linear spring in combination, now that makes a linear, is not a constant pressure problem anymore because the force of the spring changes as it moves down or up. And therefore, it changes the pressure versus volume into a linear pathway. Right? So we're looking at processes all the time. And so that process isn't really on here, but you could have a linear process between pressure and volume. That's not too bad because usually you could just think of it as the PV diagram and find the area underneath the PV diagram. The TS, thinking through for the TS thing process would take a little bit more, I don't know, a little more effort. We're not going to go beyond the scope of what we've done in the homework. Well, except to say that we didn't do every single combination of these things that are possible. But I'm not going to try to go too crazy on reinventing some new damn thing at this point. All right, so compare that homework, which is 5, to homework 6, which I labeled here. And here, I wrote out, if you remember there, I wrote out a list of the different things. And these are, we might think of as open systems. And those open systems are covered with this right here. And then sometimes we extend, you'll see that, because that total right there, we might want to go, it's not all the time, but it's only when the magnitudes are large enough of the other components, as we mentioned before, to have the velocity involved. And generally speaking, for us, we're not going to worry about the potential energy changes, not a lot. And we've even had some problems where, where I think that I showed that the velocity was just a little tiny fraction of what the thing is. So most of the time, we write this down right here, and we don't include the velocity in there, unless the velocity is really large. And is sort of the point of the thing. So that might be true for a nozzle or a diffuser, right? So the nozzle or a diffuser, generally, they might have, this one's going to be much larger than this one, and it's by the square, right? It's velocity squared. So the velocity might matter right here, and the same thing true right here. But it might not even matter here, and a lot of times for diffusers, they just say this one is so much larger than that one, so we'll just don't even worry about it, right? But this is the main equation right here that we're going to when it comes to these pieces of equipment. And that's even, okay, so velocity might matter here, except that most of the time for a throttling problem, we'll pick the points far enough away from where the velocity got really high so that it doesn't matter. And then the idea most of the time for a throttling process, which is something I'm bringing this up because it will come up again, like in Thermo 2. you'll have different pieces of equipment, especially in a refrigeration system. The valve that makes it go from being a high pressure liquid to a low pressure gas is a throttle. And that throttling process is kind of like really important. But it's an isentropic type of thing that you'll find later on. And then heat exchangers, but we pick those up in the next one, right? So 4 is important. Homework 5 is important. They're all important, but focusing on and 6. And those are what exam 2 was really mostly about. I think also we had some stuff on homework 7 as well. Yeah, we had stuff on homework 7, which is so far we have 5, 6, and 7. Those homeworks being very important. Once again, here's another heat exchanger. I don't think I asked you about a heat exchanger. I'm tempted to ask you about a heat exchanger problem. I don't know if I asked you about a mixing problem. They're not as important to me, but this can be something. You'll get a lot of stuff like in heat transfer with the mixing problems and that kind of thing, and also in heat transfer here. But you'll dive into the figure out what's taking place inside here. There was also we also did cover. I just want to mention we covered heat transfer, which I think was one problem somewhere. And I'm not asking a purely heat transfer with like the coefficient of thermal conductivity and that type of thing. That is the class heat transfer. It covered way a whole lot. Not sure if I'm doing a cycle or not. It'd be good to be able to do this, but of course you're going to go into these like a steam cycle and a refrigeration cycle. I did notice that people got confused. I'm jumping the gun here. I was kind of surprised how many people, when I asked you for the Carnot coefficient of performance, wrote down the thermal efficiency. The big difference. So let's make sure we cover that. So I probably will ask that. So I'm jumping ahead a little bit, but that is something related to this. I don't think I'm going to ask anything about these problems right here, which is like a transient problem where we're. This is sort of like a combination of this one and this one right here, but we're mostly what we end up doing is we do this type of thing into this, even though there is flow going on there. So it sort of belies the thing I just said before, but not a lot. Homework 8. All right, so here's one where we start. This is stuff that was after exam 2, and these were supposed to be pretty easy questions, right here. Where that's out of focus. I hate that. This thing doesn't focus well. It doesn't have a button. Hit focus. Where I'm just taking the high temperature and the low temperature, like the high temperature here and the low temperature there, and finding what the Carnot efficiency is going to be, and then using it backwards. I think people did okay, but here they got a little mixed up on this one, where we do the coefficient of performance instead. They're similar, but they're different. And then I thought this was a really good problem, and I only got a couple people that got in the range. But I would also the selling point of this is rubber hits the road, like real practical, like kind of things. This isn't like eggheads ask kinds of questions about that nobody will ever use. This is kind of something that you'd really want to know if you were gonna try to save some money on your house heating. You go like, okay, well here's how much electricity costs, and here's how much power you would use using trying to take heat out of the outside air. How about going digging a well instead and taking and drawing it from there? You could save some coin. It was like close to half, or right, maybe it was even more than half of money. And I also say this is like $1 per day kind of thing. People were like, wow, I don't know, you guys need to pay the heating bill at home or something. I don't know. Some of you think that you paid $28 a day to heat your house, and you're gonna go broke. You'd hope it would be in the $2 or so a day range. It's a lot of money anyway. But anyway, it's also a good learning experience when if a number result that you get doesn't make any sense, you probably did something wrong. Here was some entropy generation. I think I might include some entropy generation on there. I took a look at Dr. Yeverster's final exam. Must have been a take-home exam. Must have been a take-home exam, like way longer than mine. But some entropy generation things that are taken on, which is like more like homework 9. Well, no, this is homework 9, duh. Yeah, so we could go over some of these or some ones that are like these, or try to. It's hard to pick out some things some problems out of the book. I mean, I spent a lot of time picking/writing these problems so that they wouldn't be impossible to do, but they wouldn't also be like one line. I don't want, I don't think there's a lot of, there's no partial credit in a one-step problem. You either get it or you don't. And yeah, so, but anyway, okay, so any particular thing jumping at you in terms of particular problem, homework problem that you'd like to see? Have you looked over your homework problems and gone, I just don't see why I didn't get that right? Okay, do a Carnot. Can we? You want to do one of the ones out of here, or you want to do ones out of? I guess we'll just take a look at what we had as the homework. All right. So, and yeah, there's a particular homework I'm going to look at. Okay, so let's take a look at all of these really quick. This is homework number 8, and. So let's see what I do with the time. Did I waste a half hour? Probably 20 minutes, so hopefully 24 minutes. All right. All right, so what we had was a steam cycle with and I reminded you of the pressure and the temperature. But remember that the main equation for Carnot efficiency, and I think I put them up. Did I put them up here? I thought I put them in here. Yeah. Efficiency. There's the Carnot efficiency. It's still going to be what you want over what you paid for. And that's work net over Q net. And that could be dotted. That could be a lowercase w and lowercase q. Doesn't matter. Still, it's going to be the same thing. If you had the same mass flow, it wouldn't matter. But for the Carnot one, that ends up being, well, the work is just really the difference between the high temperature and the low temperature. So that right there is actually the same equation here, except that now we do for the thermal equivalence. So we call it a temperature scale. We're able to say and by the way, I think homework problem 1 on homework 9 really kind of demonstrated that this works. Because the part A of it, you just jump to this equation right here, which is actually this equation. Algebra works out at the low temperature over the high temperature, 1 minus the low temperature. Got to make sure that this is in Kelvin or in Rankine if you're in U.S. units. And then we went. Then I had to go step by step through the isothermal, isentropic process, isothermal process, isentropic process to complete the square, right? The little rectangle. And I even gave you a little piece of paper to do it on. I don't think a lot of people scanned that and turned it in, but I decided not to take points off for that. But those were in the instructions. Anyway. Yeah, but you could walk through it and get the net work if you figured out the work at each of the stages, the work that was done at each of the stages, and you had the heat that was coming in, the high temperature heat, and yeah, you should end up with the same efficiency that you got from right here. And it was just, I wanted you to experience it working through the Carnot. But anyway, we'll say that the Carnot efficiency is going to be 1 minus TL over TH. And for this one right here, the low temperature, really this is going to be the lowest temperature. It's going to be this 40 degrees Celsius right here. And on a ship, that's what the sea temperature is right there. We can get pretty close to matching what the sea temperature is. So some of our efficiency is dependent on how cold the ocean is. We're not as efficient when we go into the down into the closer to the equator. But when during really cold winter, we get a more efficient plant. You can't really tell, but you can, it is. And then we have the high temperature right here, which is going to be right out of there. So you're just going to be 1 minus whatever that is, 40 plus 273. I'm sorry about this. Let me pull it back a little bit. There you go. And then the 600 plus 273. And whatever, oh, that's what I was going to do. I meant to grab my calculator instead of this stupid thing. 40, 273 plus, and then 600. I should be able to do that in my head, huh? 273 plus minus. Yeah, so we're potentially, we have, let's see if I can get this even right here. What's like 64.1%. And I didn't do a very good job of that either. How do we do that? Okay, and I was also asking, estimate the increase in power if this were a Carnot cycle. And I think the power that I got out from the previous problems, let's see, I'm going to start taking these pages out because this is awkward. From the previous homework. Let's see, so remember in here we had the, well, here's the overall, we had the overall efficiency. We were asked for the power of the turbine, right? So we had 2.06 kilowatts is how much we would have gotten out before. And the amount of heat that we put in, if you recall from back here, from the boiler was 50,630, right? So, second, I should have just taken all these out. So the heat from the previous one, the heat in from the boiler was 50,630 kilowatts. I didn't need that bracket right there. So remember that the Carnot is still an efficiency which is going to be work out or net, right? But we're okay with out right there. So we would have said that what we could get out would have just been 0.641 times 50,630. Or we're going to get 32,479 kilowatts, which was much, much bigger than let's see, I think I just wrote down, or I said the wrong thing. I'm trying to oh, I see what I did wrong. I was reading the wrong thing. Yeah, no, this was the answer down here. We had 19.3 megawatts coming out. I wish that was better clear. As opposed to 32 megawatts right here coming out. So that was the point of that problem. As opposed to, keep track of that. This problem right here, where we were asking for the coefficient of performance now of a refrigeration plant. So the coefficient of performance for refrigeration, and this is the Carnot one, ends up being TL over TH minus TL, which I've written down right here. The difference between the heat pump and the refrigerator is that this right here on the top is a TH for the for the heat pump, because that's what we want. We want hot air from a heat pump. We want cold air from a refrigerator or air conditioner, right there. Refrigerator and air conditioner are identical. They're the exact same thing, just so you know. Or freezer, any of those three. They're the same cycle. They just have different, they almost have the exact same equipment. All they do is change the settings onto the thing, where the cutoff and that kind of stuff, but it's, yeah. So anyway, for this one right here, we have a low temperature, right, that we're coming from. Let me see if I want to say that, see if I'm saying this correctly, as I'm starting to doubt myself as I come along here. Where'd you go? Yes. Okay. Yeah. So we have a low temperature, and we have so it should be the 15, and we should have the high temperature, the 50. Right? Yeah, I think so. I think that's correct. Yeah. So we will go, this is 273 plus a negative 15. And if I did that correctly, that should be 258. Does that sound right? And then it's the high temperature here. But the high temperature and the low temperature, you don't actually have to, when you're subtracting them, you don't have to use Kelvin if you don't want to. And I don't want to. So I'll go 50 minus 15. And what we should end up getting is a coefficient of performance of 3.969, if I did it correctly. I'm having a feeling I might have messed this one up. Is there any chance I messed this one? You wouldn't remember, would you? Just give me a second. Why wouldn't I do that? I don't know. All right, you're being a jerk. No, I don't want you. And no one's joined us, so I might kill that thing here in a second.
Keep it for the recording.
Well, I'm already recording on this other thing, so. Homework solutions. I have updated homework solutions when I made mistakes. And no, I didn't do that. Okay, I must have been okay. So I was having second thoughts. All right. So anyway. Back to what the homework problem was asking, and so this is the coefficient of performance. The one that I had for the other coefficient of performance, just as a the one to compare it to, was like 3.68. So there wasn't really a lot of difference. That's one of the things I was hemming and hawing about. I was like, why wasn't there much difference? It was only like a 7% difference in between those. I must have, with the values that I gave you, got pretty close to being a Carnot type of thing. By the way, up here, as a means of comparison, these seem like more real values. So just an FYI. Up here, the thermal efficiency, sometimes we'll call it, was, I lost it again, 37.9%, right? So this is more what I expected. I might have wanted to rewrite the problem, but I dealt with what I had. So the Carnot efficiency was this, but for a real efficiency here, and this is actually a pretty darn high efficiency for a steam plant. In practice, you wouldn't get that. And then what I asked was estimate the increase or decrease in power required to move the same amount of heat from the inside of the refrigerator. What we would need then is we would write out what a coefficient of performance usually is. And sorry, one second. It's usually going to be QL or dot QL over dot work in, right? Because we have some electrical motors driving a compressor, and that's really what the cost of using the coefficient of performance for a refrigerator is going to be. So what you could say is if you have a particular work that you're going to use for this, which in this case, the solution for this problem was 2.06 kilowatts in, you'd be able to find out how much your Q dot L was going to be if you took your coefficient of performance for the Carnot and you multiplied it by the same amount of work in. So oh no, excuse me, I did a little mathy thing wrong, sorry. Oh no, did I do something wrong here? Oh no, yeah, no. So that's not how the problem was asked. The problem was asked for the same amount of heat moved, right? Estimate the increase or decrease in power required to move the same amount of heat. Okay, yeah. So the amount of heat that got moved, that QL, that's what we want. That's not the problem, though. Here's the problem. The low amount of heat, that should have been the 7.6. Yeah. Sorry, that was it. 7.603 was the amount of heat moved. So for this one, that should have been the work that got moved, work in, was going to be Q dot L divided by that COP R Carnot. So from the other solution, 7.603, and that would have been a 3.969, and what we would have had instead now was we would have 1.916 kilowatts compared to the other problem, which we had 2.064 kilowatts. So this was less. I was looking for a way to make get you to use this in such a way that was like a practical thing, which is to say, okay, well, here's what a steam plant or a refrigeration plant that you've already had a little bit of experience with, and I want you to go back and revisit it, but now just compare it to Carnot. So that was the point of that. The last one was to use the coefficient of performance for a heat pump as a Carnot. And that one is different by having TH over TH minus TL. And in this case, because this is the thing we want, right? And this, but TL might be something that we can control if instead of using the air outside, we use the groundwater, which generally stays at a pretty constant temperature regardless of what the seasons are. And so that's this equation right here. And the difference, I know that you have access to this. I won't write all of it down. But so in that Carnot heat pump thing, we had an inside temperature and an outside temperature, and we knew how much heat, this is how much heat the house leaks. So that's how much, if we're going to keep it at a constant temperature, that's also the amount that the heat pump needs to be able to put out. And here was the well water. So, and here was the outside temperature. The outside temperature is 25 degrees Fahrenheit. And that's one of the reasons why I was using US units for some of this, is you have probably have a better feeling for what temperature that is than you do for Celsius. So, but then when going through that, you could have converted everything into US units, or maybe it was easier to stay in SI and convert the stuff I gave you into SI. I think that's the easier way to approach the thing. But here was our Carnot, and so we had an opportunity to say, like, oh, well, here's what the coefficient of performance is when we use outside air, and therefore we have this many kilowatts to be able to move that much high temperature, high heat. I'm looking at this 22. Oh, I see what I've turned kilojoules per hour into 22.22 kilowatts. Okay. So now here's how much power it costs, and then here's how much it costs per day to be able to do that with the heat pump. But then here's with the well water. You can see the coefficient of performance is so much higher than it is with the outside air. But notably, you can't achieve this coefficient of performance, but you can't achieve this coefficient of performance either. These are ideal conditions, right? It's impossible. But a lot of problems that are similar to this will say, this real world heat exchanger, heat pump has a coefficient of performance that's 25% of the Carnot one. Like, okay, so this as a point of reference. But you can see how much you could save per day. And so if you were to say that, well, this 25% of this or 25% of this, then it would still give you the same kind of relative breakdown of cost, where this one is just under half, or this one is just under half of that one per day. So using well water made a heck of a lot of money savings, and the cost of an investment and that kind of important stuff. As an engineer, I have to deal with money all the time, as well as numbers, although they are numbers. Okay, so anyway, I'm not sure if that was helpful, but I'm going to try to continue with more helpful things. Let's see, that was homework. That was from homework 7. It's homework 8. I was thinking about taking a look at homework 9 a little bit. Homework 9? Okay. We'll talk about some things that maybe were commonly missed. Yes, sir?
For the thing, is like the concept for the exam going to go up to homework 9? Or
We could do stuff on homework 10, but it's, I don't think I would do anything on the fourth problem in homework 10, but I think homework 10, the first 3 problems aren't totally unreasonable, because I'll show you what I mean in a moment. Is that okay? Yeah. Delayed gratification on the thing. Yeah.
How long is it going to be? Like, before you were saying that it would be like long, like a lower amount but longer problems versus more problems that are shorter.
That's exactly right. I don't know right now. I will know. I mean, I kind of wish I did, but at the same time, I want to leave myself the freedom to decide late tonight, where I'm like, oh yeah, all right. But I don't want. I'm not trying to fill up the time, the 2 hours. Mostly, I'm trying to like make sure that I'm doing an accurate measurement in my mind of what of success in the class. And so if I could do it in 4 problems, I'll do it in 4 problems. But I'm thinking it might take 6 problems. if I want to cover everything I did, but I'm going to time myself in a variety of different for a variety of different problems, and then try to see what a reasonable amount is. I usually try to use a factor of 2.5, somewhere between 2.5, sometimes 3, where I'm going to go like, okay, if it takes me, if we work backwards, what does that say? If it's 2 hours, let's go like 100. Let's go 120 minutes, and I divide it by 3. So I could have done that in my head. So if it takes me 40 minutes, I go, okay, that's probably the right amount of time for this. So if I could do 6 problems in less than 7 minutes each, so like, okay, that would be acceptable. But if they take me more than that, I might reduce it down. All right, so let's see. All right, so I already mentioned this problem right here. Now that problem's way too long, but I did see that a lot of people struggled with it more than I thought they would, which really, here's, by the way, this is what I wanted. I wanted, you didn't have to print out in color. But some people just kind of sketched it over to the side, which I decided that's good enough right there. But I do want people to be able to, or I do want you to be able to, like, look through each of these processes, like to go from, so we're going from 1 to 2 to 2 to 3, 3 to 4, right? And so this is a heat engine. You wouldn't go in this direction for a refrigerator or for a heat pump. Going to put me on the spot to try to remember which directions you start on. It's usually at the, I think you usually start down here in your process and you compress. All right, is that true? I'm trying to remember which way you go right here. Where you go, no, maybe no, this is it. I think you go compression up to here, right? And then you cool it. No, that's got to be, it depends whether it's a heat pump or a thing. So this should be the high, yeah. This should be the high temperature heat exchange right here because of the TS diagram. But you come up here isentropically, and then you expand it, and then you cool it right here. So this is where the cold heat comes flowing into the process right here for a refrigerator. And this is where the hot air gets put out for a heat pump onto there. But to be able to think your way through a Carnot cycle, and to be able to work your way through, and that's no pun intended, well, across from here to here on the TS diagram is pretty easy because it's just the area underneath what's happening right here, right, to get the Q. It's going to be temperature times the change in entropy. And the same thing between here and here. To get the big QH is going to be the area that's underneath this line right here, all the way down, right? So it's going to be the temperature that this is occurring times the change in entropy. Whether you're going one direction or another, and that's depending on whether it's a heat engine or if it's a refrigeration heat pump. But that's, and you're also able to navigate the charts, the tables, to be able to get what those values are of entropy. But also to go through and apply on each of these processes, right? So you go use this first law for a small chunk right here, and U2 minus U1 is equal to Q1 2 minus work 1 2. Right? And so for between states 1 and 2, we have nothing is 0, right? So even though we already have the heat that's taking place right here, which is going to be what we found right up from above. Let's see if I did that right. I am being a liar. No, yeah, right here. 23 right here, so that's the Q, and I got it from up here. And then you're able to find out what the work was. And the same thing's true with each of these processes, and you find out what the net work was. So here's 4 different networks that you get from each of the processes going through each one. And then you're able to get the network and divided by the heat that was supplied from the thing, and you're able to get what the same Carnot efficiency. So I referred to it before. I talked about it, but I figured I would also show what we had talked about. So we should be doing some more problems, should we? I don't know if this reading through these things helps. All right, so here is one. No, that's not true. Okay, now, okay. So here coming up with an example of a problem I might ask. So I'm going to jump to it, as Alex had asked for. One that I was surprised, and I had mentioned earlier. All right, so this guy right here. I was surprised that no one got this. So maybe I'm going to work through it one step at a time, as opposed to just showing the solution to the thing. All right. And this one does have entropy generation. And Dr. Yevistruk on his final exam had a lot of entropy generation stuff. And though I know, even though Dr. Milanovic hasn't covered it, I do think it has merit in demonstrating whether the stuff that we've gone over has worked. That wasn't Alex, that was. All right. All right, so this is problem number 2 from homework 10, where we have a cylinder with stops and 0.2 kilograms of water, and we were given a temperature of 500 degrees Celsius, and the piston makes a good seal. All these words meaning that this thing is going to keep a constant pressure until it hits these stops, and maintaining a constant pressure of 1,000 kilopascals due to the thing's weight. The stops are at 1/2 the volume of the cylinder. Heat is removed until the water is 25 degrees Celsius. Determine the entropy generation. So as we go through this, we don't know for sure necessarily all the things that we need as we're going through, but we can kind of march through and collect some things, and maybe we'll get some things we don't need along the way. But you know, it is a challenging problem. So I'm not like judging, but just pointing out that we had some issues. All right, so. All right, not to scale. And we'll start at the beginning. I'll call it 1. T1 is equal to 80 degrees Celsius. I also said that P1 was equal to did I say 80 degrees Celsius? I think I just worked the wrong thing. 1 second. I was looking at the wrong guy. 500. That would make more sense. 500 degrees Celsius, and P1 was 1,000 kilopascals. And okay, so the V right over the side. V2 is equal to 0.5 V1. Oh, and we also had a mass of 0.25 kilograms. And at 2, T is equal to 25 degrees Celsius. All right, so we go ahead and from table, We're not quite sure which it is, but it would be quick to look up. We have 500 degrees Celsius and 1,000 kilopascals. I can kind of guess that's going to be superheated, but we want me to double check first, right? And it turns out it is. So that's like B.1.3, and we looked the thing up at those, and we get V1 is 0.35411 cubic meters per kilogram, and we don't know if we need it yet, but let's go ahead and get U1 because it's a chunk, right? So that's a chunk of mass. There's a good chance we need it. We don't need these many sig figs, but I'll write it down anyway. And we're talking about entropy, so we might as well write down what the entropy of this state is. There's a good chance we need it. That's supposed to be a kilogram degree Kelvin. All right, so we kind of have to, like, it wouldn't hurt us to think through what this is going to look like, right? So the first thing, so maybe a PV diagram might be a better one to start with, right? Remember, it's water, well, or steam, if you will. And so it's got a vapor dome, and it's superheated. So it's outside the vapor dome, and we're going to have a constant pressure process until it gets to right there. So I'll draw this as a dashed line, and we might even want to call that, we're going to call that point A when it hits there, right? So 2 is after all the heat has been removed to get it down to 25 degrees Celsius. But it's going to get to somewhere in here, we're going to guess, you know, going a straight line at constant pressure until it hits the stops at A, and then it's going to start coming downwards. So it hits 2. So that's kind of the idea. Looking at this thing should make you think this thing. And so V2, same thing as VA, because it's the same mass, so we don't have to actually find the volume. We have the specific volume, so that means the same thing. It's going to be 1/2 V1, which ends up being 0.35411, and that ends up being, I don't need a parentheses, 0.1771. All right, so because we have this value right here, we can look up, and it's a constant pressure. We can try to figure out, well, first off, we're not 100% sure that it isn't still superheated. There's some, maybe this was so far out to the right that it went down. It was getting a smaller amount of volume, but then it hit before here. But there's a pretty good chance that it's going to be somewhere in there, in that range. So what we would do is we'd look up in, I didn't communicate that well. There's a pretty good chance it's going to be, it's not yet a liquid, but it's still not superheated. So that would mean we would want to look up in table B.1.2, which is the pressure indexed one. And it's at 1,000 kilopascals. So we come into 1,000 kilopascals, and we look for a specific volume. And we just said that it was 0.1771, and that's in between. So now we can find out what the quality is going to be, right? So we can look at table B.1.3 at P is equal to 1,000 kilopascals. Tsat is equal to 179.9 degrees Celsius, if we want to know that. And from the VF of 0.001127 and VFG of 0.19332, we're able to get, using this, right? So we're going to use V is equal to VF plus X. Let's call this XA, VFG. So this is going to be the quality that at that stage. So here's a 0.1771 equal to 0.001127 plus XA, and then the 0.19332. And again, XA is going to be near 90%. Well, wait a minute. Oh, you know, everything I was about to do right now, I forgot. This is like a time waster on an exam, unfortunately. It was a time waster for me when I looked back and reflected. I'm like, oh, I don't actually need these properties. If somebody had asked for them, then I would need them. But this is all just for information, 0.9103, right? But it's not needed, so I'm sorry to waste your time. I just noticed it myself. Not needed, but you could have done it. And you'll see in a second. We'll make sure we point out why it's not needed. And you could have gotten all the other ones, right? You could have figured out what the internal energy was going to be, and what the entropy was going to be in between these things right here, right? So they ended up being 2,426 kilojoules per kilogram, right? Just using out of the same table, out of that same section. You could also had 6.187 kilojoules per kilogram degree Kelvin. But still, both not needed. But it is a two-stage. You did need to realize that you had a constant pressure process and a constant constant volume process. Now, okay, so that was all at A. So now we're going to go down to 2, right? So what happens at state 2, and it's going to be keep on removing heat from that one place to another, and so we're going to go back to table B11, and this is going to be at the T is equal to T2. It's going to be equal to 25 degrees Celsius. PSAT, by the way, if you care, is 3.169. So this is a whole lot of vacuum going on right there. We do that same thing we just did a second ago, but now we're going to do it for at this temperature, at these properties right here. So we have the volume 0.001003 cubic meters per kilogram. It's close to, 0.01, which is what we expect. 0.001, what we expect for like what water typically is. VFG 43.359, whatever. And that same idea that we were doing up above, this is the same specific volume at this point as it was at that point, which is this 1/2 right there. So it's here we're going to use that specific volume along with V is equal to VF plus X. Now this is X2 VFG, and take 0.1771 is equal to 0.001003 plus x2 and 43.359, and find an x2, which is going to be equal to very, very small, 0.04061. This is barely steam at all. And from that, you can find what U2 is going to be, and that's 1,001. No, not 1,000. It's 114. 114.2 kilojoules per kilogram. And S2 from that same section is 0.4006 kilojoules per kilogram degree Kelvin. The problem asks for the entropy generation. How much entropy generation do you have? In order to find the entropy generation, maybe you should write down that equation. Where did we go here? Yeah, right here. Okay, so it's this guy right there. Let's write it. S2 minus S1 is equal to the integral of Q over big T, or I think they go, I guess they're okay there, and plus S-gen. S-gen's the stuff that we can't get back. It's just the inevitable part of this world, and it's the irreversibilities, the true irreversibilities. So we need to get this Q. In order to find that Q, we're going to use the conservation of energy equation, right? And it's for a chunk, so we're going to go big U 2 minus big U1 equals Q 1 to 2 minus work 1 to 2. Well, we have this end. We have these end states, right? We have Q2 right here, and we have Q. I said Q1. I said U1. U1. Oh, U2. U2 right here, and then we also have U1 all the way up here. We also could find out what the work is going to be, but no work is being done between A and 2 here. Only work is being done because this is a constant volume thing that takes place in the second stage. So let's find what the work is going to be. I'll do it over here. Work 1 to 2, which is going to be integral P dV, but in a constant pressure system, that's just pressure times volume change, V2 minus V1. I want to keep the signs straight in this, and we note that this thing has weight, and it's kind of pushing down onto the thing. So that's actually, the weight is acting on the water, the steam. Therefore, you should expect this to be a negative number, because work is generally going to be outward, right? This is inward. Work is being placed onto the thing. So, and also, we're using specific volume, so we would really want to write mass times pressure times V2 minus V1. Make sure you're keeping track of your units. Sometimes they could be the indication, right? They should be able to cancel each other out. So if you didn't, sometimes you don't need to multiply by mass. I can show you an instance recently, the equation that we were using, where you didn't have to use mass into the thing if you used one version of it. But I saw a lot of people making that mistake and forgetting they had to multiply by mass. I'll show you what I mean in a minute, hopefully, if I can remember. So anyway, we were told that was 0.25. The The pressure was 1,000 kilopascals. That kilopascal is going to help us out because that's actually 1,000 newtons per square meter, and we're going to multiply it by a cubic meter divided by kilogram. So that kilopascal is going to make a kilojoule, just as the way we have it written. So if we just leave it as 1,000. And then we use the volume that we had, which is going to be, and actually right here, because one of them is 1/2 of the other, we could have like cheated and just write 1/2 next to the original one, but I'll write it out, even though I'm running out of room. 1771 minus 0.35411, right? Just to reiterate right here, this is a cubic, maybe I'll write underneath it, cubic meter per kilogram times a kilonewton per meter squared times a kilogram. That's why we're able to get out of this thing is going to be a kilojoule. See if I say this right. Yeah, because we're going to have kilonewton meters, right? Which is a newton meter is a joule, and we're going to have 1,000, so we're going to be okay. So this ends up being negative 44.28 kilojoules. And so up above, I'll write it out in a simpler way here. These need to be capital U's, but we've been given, but I found some lowercase u, so I need to multiply mass by it. So you'd go m times u2 minus u1. It's going to be equal to q12 minus work 12. Remember, that is minus, so those minuses are going to cancel out. So we have 0.25 times u2, which is 114.2. Put the brackets in there. Minus u1, which is all the way at the top, and that is 3,124.3 equals q 1 to 2 minus 44.28. And so we have a Q. I'll go to a new piece of paper. I should have done it a while ago. I was trying to cram everything in there. Bad role model is what it is. What's that?
Yeah, I was looking through it to see where like I went wrong, because we had close numbers, but it wasn't. I was like a little bit off, and then I realized that I added work
Okay.
to it. I was to subtract it because it's double negative.
But you understood. I mean, you were following with the.
I got the whole process right there. I messed it up.
Oh, okay, it's hard to. I'm not sure if I graded that accordingly. I mean, most everybody's. I tried to pay attention, but if your name gets near the end of the sometime end of the alphabet, it's not as. You get the short end of the stick when it comes to grading sometimes. Well, sometimes it randomly grades. It puts the names randomly. I don't even look at what the names are, but I'm just telling you, my attention span starts to, my endurance. So anyway, coming back over here. All right, so we want to go back to this equation up above, and this is the thing we're looking for. So we could rewrite this thing out, I guess. We go S gen is equal to S2 minus S1, and that's going to be minus Q12 over T. And so remember that these are capital S's. We have lowercase s's, so we need to do M S2 minus S1 minus our S1 to 2 over T. So that 0.25 S2, if you recall, 0.4006 minus S1 which was 7.7621. But then we have minus 796.8 divided by temperature. Here's an important one. I should have used the phrasing for any of these S-gens that we can say that the barrier of this was also at 25 degrees, right? So in the problem statement, should have been saying that the barrier through which this heat has exchanged was a particular temperature, because that's the temperature that belongs right here. When it talks, when the heat is passing through a boundary as you're treating it, that is the temperature that should be in it. So this is the 273 plus the 25. And this generation should always be a positive number. I think you kind of effed up if you messed up somewhere if it, for whatever reason, it's a negative number. We should be always generating this right here. Now, you know, and I think some of the importance of this concept is that this right here, this S2 might be a smaller number than S1 and give you a negative. But then this process right here will return it to being a positive thing. You'll always be generating entropy.
So when we do this equation, the T that we use is the state we were going to?
In some of the problems, I actually will make it like very specific right here. And this one you kind of had to either email me and ask me because I forgot to put it on there. Or there was a phrase, I think, on the original problem that I looked at this. It said, like, assume that the surface through which the heat is drawn is the same as ambient, which is the 25 degrees, right? So, yes. But you might recall some of the heat pump or air conditioner problems where I say, okay, well, the fins of the heat exchanger were a particular temperature, right? That is the boundary through which it goes, right? So if you were to take a look at let's see if it was, yeah, the last problem from this section, I said that there was a outside temperature, but there was also a temperature at the heat exchanger, right? But it makes sense because you're always going from a high to a low. So if you want to be able to draw heat from the outside, this is a heat pump, right? This thing needs to be a lower temperature than that thing, like the surface on the actual heat exchanger, the fins onto the thing, the thing that you would touch with your hand, right? If you would say, wonder how warm that is, and that's always a bad idea, right? You should use the back of your hand. Here's a life lesson. If you want to know how hot something is, use the back of your hand, because this will save your life. If there's a fire, I think there's a fire on the other side of the door, you don't test the door with the palm of your hand. You test it with the back of your hand. Because you can still use this hand if the back of it's burned. But you can't use this hand once it's been burned. So you just took away half of your hands if you burn hands. There's a little life lesson right there. If you go to firefighter, I went to firefighter training. Everybody at sea is a firefighter. There's nobody gets to run away from the fire on a ship. Everybody's a firefighter. And you'll be dead in, as you're in there. Anyway. So anyway, you run towards the fire. Anyway, so yeah, that temperature, like right here as well, on this side of the thing. So when I was asking this problem right here, that's actually a good segue into it, where we're looking for a Carnot heat pump, right? And once again, lots of people are writing when they say Carnot, they wrote the efficiency equation. This is the Carnot heat pump coefficient of performance equation that you want to put in there. It's not an efficiency, it's coefficient of performance. Hammer that home. And for whatever reason, Word decided to get rid of there are numbers in my Word document right there, but it gets tired at the end of the semester or something, I don't know. And it just will not print these to PDF. It just refuses to print certain numbers. I don't know what's special about them. I had figured it out at one point, but don't know. But anyway, so this is, the summary of this is more interesting than the actual execution of it, because you can now see where entropy is being generated throughout this entire segment, right? So we're taking outside air and we're coming through here, right? So heat is moving from the outside into the heat pump, which I've made look like it was attached to the side of the house. And work is being put in. Of course, it's not coming from there. It should be coming from from an outlet, an electrical outlet. And then and then the heat is leaking out, right, into the world. So you could see, if you go through this, the process as you're going through, you have the same, you should have the same, this is the same QL dot that is drawing from the outside world. It's being passed from the outside temperature, so it's going from, looking at this equation right here, you're going from the outside to the inside, okay, and the sign comes from which direction it's coming, either into or out of, right? So this is going into the heat pump, and this is coming out. See if I'm going to say this the right one. QL. Okay, so summarize of here, where if heat comes.
What's
TA, I just had to name it something. It's to the surface of this right here, right? So it's not. This is actually a lower temperature than this, so I didn't want to call it TL. The surface of the heat pump has to be a lower temperature than the outside air. Otherwise, it won't move. The temperature on the outside has to be a higher temperature. It's from high to low. So anyway, marching through here, each of these things, you can see there's a positive generation rate coming on every time. And I think did I write kilojoule? I got that right. Okay. So these are, and I made these watts instead of kilowatts because they may get really, two more decimal place things over to them. It looks kind of silly. So just making them watts made more sense. But you this one and this one and this one and this one. I should have kind of asked, what is the total? Because that kind of looks from the outside, from the very beginning, right here. So you have that guy and this guy, right? So we had this is actually coming in and this is actually going out. And when you end up looking at the thing, you get this amount of generation. But if you were to add up this, and this, they equal this, right? In terms of the conceptual part, that they all add up to the same thing together. We're generating entropy at each stage of the thing. When we come into the heat pump, when we come out of the heat pump, well, when we're inside the heat pump, excuse me, when we come into the heat pump, we're inside the heat pump, coming out of the heat pump, and then coming out of the house. Each of those heat transfers and processes within inside the heat pump generates entropy. And therefore, we've generated this much entropy. And that's sort of like the conceptual thing that says entropy is always created. Well, here it is. But we can go to the left on a TS diagram on something. That doesn't mean that we've somehow gone negative entropy. It just means we've transferred heat. Anyway, it was an important thing to me because that was something, after years of being a practicing engineer, I couldn't remember how the hell we got away with that on the TS. And I just went ahead to hit the accept button. And for me, it kind of scratched an itch. It was important to me. So one of the, I alluded to something with whether you want to include mass in, or cautioned you about including mass. And it was really about the polytropic, or it was either a polytropic or an isentropic work problem. Because, and before I go any further, make sure that we know that when we're looking at these equations, we look at the context, that this is an ideal gas and a constant specific heat. but I saw a lot of people jumping from work to this process right here. And while that's true, it's sort of I'm worried about plugging and chugging, so make sure you're not just a blind plugger and chugger of values in there. Recognize that alone right there is still a per mass basis. Like cancel out the units and see that ends up, But this one, most of the time these are written as capital V's, and if that's the case, you don't need the mass right there. So sometimes we were given a volume, and we knew what the other volume was going to be, and we could find the work directly from there. So do you write down both versions of the equation? No, you just remember the context of of what it actually means, what it's actually used for. So some polytropic processes, or running through some problems that deal with these different types of processes, is something worthwhile. And a lot of them are covered in, as I mentioned, well, there are some that in homeworks. Let's see if I say that right. Is there some? Yeah, there's some in homework 9. So some review of homework, looking through problems in homework 9. And then there was actually a couple. There was one in homework 3, right? I mean homework 10. Excuse me. So we did that. We talked about this one. This is a rigid one, constant volume. Also in homework 9, we had some. So we had to find find the work performed and plot the points. So those are important right there. We have an adiabatic one because it's insulated cylinder is a reversible process, right? So this was an adiabatic process in that one. All right, so can I take our requests? I can just keep doing problems. No? Yes? Okay. I'll just keep doing problems. What's that? I will. I don't know what's going to be on the exam. And I just had to try to, I had to do things in a certain order this weekend, and that was the last thing in my order. Yes, yeah. I had, and I'm required to get all of my finals done in 48 hours, and I got them each done. I got the grades in.
Why are you required to do that?
They send me a note that says I have to,
No one else does that.
but they sent them that same note. I don't walk across the grass. But it's against the rules. Somewhere.
Not here.
At the Merchant Marine Academy. You don't know how much scar tissue that place. Some things I just can't do it. But I can speed. I'm totally okay with speeding.
Yeah.
I'm a serial speeder. Almost got caught. Did not. Learned my lesson? No. Don't care. Not done.
You ever got a ticket?
No, I have.
That's what I said.
I got a lot of warnings.
But you cry when you point
No, my wife does though. She says I'm not a feminist when I get pulled over for. She says I'll cry. She'll curse first though. Ooh, that woman's got a mouth. All right, so let's see. I'll do stuff on here. I'll do problem 4 first, right? Where we had a piston, oxygen at temperature 227 and pressure 600 kilopascals. It is changes. What's up with the grammar? Like the Grammarly's let me down, man. I don't know. Is changes volume following a polytropic process with exponent n 1.24. Oh, that was actually one that really everybody bothered me. Like there was a problem where I asked for an exponent of one on a polytropic process, And people just wrote down 1.4. I'm like, are you serious? Come on. I telegraphed that. Resulting in a final temperature of 477. Treat oxygen as an ideal gas with constant specific heat. And we want to find the final pressure and the work in kilojoules indicating in or out, and the heat transfer in kilojoules indicating in or out. Okay. And this is in 9. How come I don't have anything with entropy? There must be something about entropy involved in this. And I just can't recall.
Homework 8.
It's homework 9. Homework 9 does seem, yeah. Homework 9. Problem 4. So, I like to write it down. Helps me think. While I'm doing it, I gotta tell you, this is usually where where it starts to dawn on me what I'm giving, what it is that's the problem's really asking me to do. And all right, so we got 3 kilograms. We got a temperature 1 is 227 degrees Celsius, which is 500 degrees Kelvin. They told me P1 was going to be 600 kilopascals. They said that it was polytropic, so 1.25 is my exponent. And my P1, and I think the next thing I give you might be an unnecessary piece of information, maybe. No, I just screwed up. I don't know what the hell I wrote that for. All right, so T2, that's what it was. 477 degrees Celsius, 750 degrees Kelvin. And our find was P2. The work and this. And I don't think I need, I guess it was just a polytropic process. It's interesting, because we covered a polytropic process way back. So just redundancy, just more usefulness. Anyway, if we were going to use our equation sheet that ran away, where'd you go? There. It would help us to remember, oh, a polytropic process. Okay. It has P2 over P1. But we do know. Okay, so we know what the. And this is O2, right? So let's go to find out table A5. We'll find that oxygen 0.2598 kilojoules per kilogram degree Kelvin, and CP is equal to, might not need the CP. CV might be good for us. I wonder why I asked this one. Okay. So we'll write out the T2 over T1 is equal to P2 over P1 N minus 1 over N. You could also reverse this if you want to. P2 over P1 is equal to T2 over T1, where now you have N over N minus 1. Right, just flip this thing upside down as you're doing the thing over. So we could get P2 is equal to P1 T2 over T1. Well, I just wrote that, dumbass. Oh, I guess I'll write it again. N over N minus 1. Almost called myself a dumbass. Oh, very nice. We know what the temperatures are going to be. And these temperatures, remember, these need to be in Kelvin. So we're going to go, T2 is 750, T1 is 500 in Kelvin. So you go 750, 500, and that's 1.25 over 0.25. So we'll get 4,556 kilopascals. Lots of people got that right. Here's where people messed up a lot, quite often, is they were looking off of whatever equation, probably off of the cheat sheet thing, and they decided to go with the temperature one, which isn't a bad idea because we don't know anything about the volume on here, right? Because you know, in terms of our equations right here, we have two choices: the polytropic with P2 V2 minus P1 V1, but we don't know any of them. We could find them. That's a chance. You know, we could find them because we know the R, and now we know the P and the T for both of them. So we could find the V1 and the V2, but we could take a shortcut and say the work between 1 and 2 is going to be mass times R times T2 minus T1 over, and they're going to be careful of this, 1 minus N. Oops, sorry about that. And remember the signs, we're going to try to keep the signs correct as part of this. So the mass was 3 kilograms, R was 0.2598. We had T2 was, I guess it doesn't matter which one we, you know, you don't, this doesn't need to be degrees Celsius because we're taking a difference. And, whoops, 1 minus 1.25. So that right there is going to make it a negative. But that's expected because P2 is greater than P1. So we have compressed it, so work has gone in, and by definition, that is in. Negative is in. And therefore, and we were trying to, so we found that's part B. And part C, we need to go to the first law, U2 minus U1 equals Q12 minus work 12. And so we could really write that out again this way. And these are going to be per mass. Well, actually, we don't, we can go constant specific heat. So we can go M, U, oops, CV, T2 minus T1. And then it's plus work 1 to 2. CV 0.662, and this is 750 minus 500. So also negative 282.9 kilo. So in order for this, you know, polytropic thing to work out and to behave this way, we have to be removing heat at the same time while we're adding work in. So work is being added in while heat is removed. So that's why both of them are negative.
Should put this on the exam.
You need to include the work.
I can't hear you.
You need to include the work.
This right here?
On the, no, the bottom, like the line that's off for Q, you didn't include minus.
Oh. Sorry. I was ready to be done, so. If we wanted to instead, because this is oxygen, we could have, and I might ask, I think I would likely ask a question somewhere that you could compare. I had several times the constant specific heat result to if you had it in from getting them from tables. So you know how I would do that in this one? And I think I meant to. I think I meant to make this problem a lot longer, looking at it, because it seems out of place right here. And I also noticed that my temperatures were even numbers.
You don't like,
Excuse me?
you don't like that they were even numbers?
No, I meant them even, so that you would look them up in a table. And I'm not sure why I didn't. So I think I was writing this problem with the intention of having you look them up and compare what your results would be without constant specific heat.
Which table would that be? That's like the first one when you enter section A, right?
It's in the A section. I'm about to look it up here in a second. So for this one, I think it's table A8. There's nitrogen. There's okay. So I think it's A9. I think this is right. Well, let me check. It'll be this one right here. Maybe no. Maybe earlier. Right. So this is the one where we had the enthalpy, and they have that standard entropy. But I think A8 actually. Yeah. Here it is. This one. So that would be the O2, and we'd be able to get the U's from this. So if you did it, because I picked up, what was my temperature? Yeah, 500. So I have, so that's U1 is 331.72, and U2 was 519.02. I might have tried, I was thinking about maybe doing something with the entropy. I'm trying to remember what it was that I'd want to say. There was entropy generation. No, that was only homework 10, right?
Homework 10 was entropy generation.
So we didn't have anything that was like, find the entropy. We didn't do a lot with entropy in here. I wanted to use that standard entropy thing for something. Although now with Dr. Milanovic, I'm not sure what she will. I'd like to see what her exam looked like.
I know the 3 questions to look up.
Maybe I'll ask you later when we're not being recorded. 6.8969. I know, sorry, this is boring theater here. I tried to be more entertaining. Maybe next semester. 7.3051. And specifically, one of the things I would like to have used more often were the Gibbs equations. I don't think we had many problems, or hardly any problems, where we used these.
Why do you want to use them?
Because I know that they're useful, and they might be useful next semester. And I don't think I honestly, firmly believe this, that as an engineer, just being told something, maybe they could do it in other majors. Maybe in other majors, when someone tells them the thing, and then they ask them on a test about the thing, that's totally fair. But I don't think it's fair, or that you remember something, unless you use it for something. Like you use it for a calculation, then have a chance for it to stick, or then use it repeatedly for something, right? To have some type of use for it. Why bother learning something if you don't use it for something? And that's so we learned about this, but we didn't really quite use it. But you could see you could find out what the enthalpy, I mean the entropy generation, what the entropy is going to be based on these, or we could use this thing right there, right? So I think that's what I had intended on this problem. I don't remember, but anyway, regardless, let's see. Yes, we're gonna do more. I just want to double check and see how much of a difference this would make right here, this portion of it, because this is the only portion that would really matter right here. Is in you go or, and I might have written that in a solution somewhere. I don't know now. Q1 to 2 was going to be equal to 3 times my 519.02 minus 331.72, boom, and then, as I had forgotten to write it up here, plus minus 779.4, just to see what the differences are going to make. And 519.02, because I don't have the in-between numbers, I have to write the whole thing out, right? 0.72 minus 3 times, and then 779. Yeah, so now I get a minus 217.5. That's a pretty big difference between the. So I would say that the constant of specific heat is deviating somewhat from the actual values. All right, yeah, so more problems. Let's see, maybe a flow problem. Those are actually too hard. Heat exchanger problem. A compressor going into a heat exchanger. I gotta tell you, you'll probably see a compressor going into a heat exchanger. Dr. Deal loves himself some. Or a turbine going into a heat exchanger. I like combining things together. That's because I want to teach Thermo 2. I would rather teach Thermo 2 than Thermo 1.
So that counts like a mixing problem or just combination?
Just sort of just a combination. So you got to go.
So that'd be like I say like 1 to 2 and then 2 to 3.
Yeah, kind of thing like that. Yeah, yeah. But not the mixing problems usually when you're. I'm trying. Now I can't. Words don't work. I was going to say it means two things mixing. It's just you can't use the definition of something for the definition of the thing. Okay, so no, I'm not going to try to be clever. I'll just go with what I know. Thank you for your patience. 1 second. The homework 7. What'd you do? 7. Yeah. Oh, what did I do with it? Somehow. There you are. You were there. Okay. I don't have any creativity right now. Doesn't match well for you. All right, so let's say that I want to condense all right, so I'm going to invent a problem where I have this steam turbine right here, and we're going to figure out what the flow rate needs to be of the water coming out of the condenser from this. We'll find out what the water flow rate, if I only want like a 10-degree temperature rise of the seawater. Now, why only 10 degrees? Because we don't want to hurt fish, and we make a lot of hot water. Fish don't like the hot water that we don't. So it's like thermal pollution that we've been doing for a long time. So we want to make sure we have enough seawater passing through our condenser. And all right, so here we go. So let me get I need the cheat sheet because I want to, so it'll be more efficient. So we have these conditions for our turbine. We always draw a steam turbine as if it's getting larger. Of course, I didn't do a very good job of it here. Here's the shaft coming out, rotating right here. So we have the inlet at 1 and the outlet at 2, and then it's going to come into a condenser, and they actually sit on top of each other. You couldn't really identify that the two things aren't like built together on top of each other. You don't see this pipe. But here's the condenser. There's a little well at the bottom right here, so we can. And it comes up here, and so here's 3, and then there's a pump right here. A special pump because it wants to cavitate. We want to know we're going to have, and as a cadet on board the John Likes. See, this is actually what this thing looks like right here, by the way. Right here. It's got thousands of little tiny tubes. Like that right there. And this end comes off. Also, there's little manholes to come into there. And they stick the cadet inside there with a little air hose with a little valve on it. Little tiny, it comes out. And I had to push air through each one of these things to knock out all the slime and sludge, and there's little tiny crabs and stuff crawling all over it. And it had to be covered in like a Nomex suit, and like but then you like smell you just wouldn't believe the smell, and do that like for I can't even remember how long it was for. Sticking the cadet inside the boiler, and instead of the condenser, that's what's fun for merchant mariners. All right, so. We already did this problem, but it's been a while, so you would have forgotten it anyway. So we have the pressure is 1,000 kPa coming in. Temperature is equal to where'd you go? You lost me. 450 degrees Celsius. We can ignore this velocity, or we can relearn again that we can ignore this velocity. That he's not very much. Yes, sir.
So isn't this more similar to like homework 7?
Yeah. It's actually homework 6. Was there one in homework 7 where we did this?
Yeah, homework 7 was like the whole like the stringent processes.
Yeah, but it was it's like similar to this portion of it.
So would there be a problem where we have to focus on like being tired?
No, if it takes so much time, no. If I could figure out a way that I can work through one, and I can, anytime I like take it, by the way, I usually try to turn my professor hat off. It's kind of hard to do. I've been wearing it for a while, but I'm pretending I'm a student, and that like I'm approaching it without already knowing what the problem's about and that kind of thing. Try to slow myself down, but it's impossible to do, like 100%. But I think an entire cycle would be too difficult unless I gave you like the answers to a lot of stuff in there. I gave you a lot of information, but still, then you have to read it, and that takes time. even just reading the thing and recognizing that you don't need to find something can be kind of a cruel trick to be playing. I'm not looking to make cruel tricks. I can accidentally make things that like I didn't realize that would cost somebody, more time to do. But I don't know. It sounds like I'm making excuses. I'm just trying to assure you that I'm not out to get you, but just trying to extract out, see how did everything work out? How are you doing with the mastery of the material? So P2 was 10 kilopascals, and we have we're given and the quality, so it's still 92% steam, and V2 is equal to 50 meters per second. And looking at, let's see, we'll look at the time. Oh, okay, so I'm going to go too much further into overtime. I know you guys have other things you might have to prepare for. How many people still have another exam besides this one? Okay, well, good. Yay. That's got to feel kind of good, except for mine. I'm the asshole now, right? Okay, well, I'll live with it. So we have 12 kilograms per second. All right, so the things we would want to typically find here, make sure that you could find the power. That guy right there. I don't know if I care about this part right here. I don't care about the turbine inlet diameter. I don't really care. I could also ask for what the diameter of this is going to be, or the diameter of that, either way. So I'm not going to ask that. I would rather need to know C delta T has to be 10 degrees Celsius of seawater. Now, our first question is seawater even in the book as a property? It's in all of my books, but I went to a different school. Anything else I would need to know? I don't think so. All right, so I want to go the mass flow of seawater. So we'll go through this without looking up every damn thing in the book. So you go at 1. All right, so at 1, you'd be able to find. Well, let's write the main equation down and then get this stuff. So here you go, put this on this side. So the main equation of what we want, and that would be our all-important first law, and it's this guy right here. Where we're going to write 0 equals Q, 1 to 2. Give them a dot. Doesn't matter if you give them dot. You can leave all the dots off as long as you leave them all off. And we'll call this I and HI. And they said the equation as I wrote it down was like theirs, and I wrote the tot. So M dot E HE tot. All right. So we need enthalpy. That was my point right there. We need to find what the enthalpy is at the conditions at the inlet of this thing. So we go at P equals 1,000 kilopascals, and T is P1, 450 degrees Celsius. We look this up, and H1 H1 is 3,371.2 kilojoules per kilogram. And we had to interpolate, unfortunately, for that with the value I used. I'm not sure if I did that on purpose, but if I did, I don't like myself very much, but that's okay. If we were going to go ahead and mess around with the areas of the thing, we would need to know this right here. I'll show you what I mean. or you could see it in, later. Anyway, so we got these 2 points. Then we have to go at 2 right here and find. We were given the pressure, so this would be at P2 is equal to 10 kilopascals. We would look that up, and using the X 92%, we would be able to find what our V2 was going to be. I don't think we needed to know it, but it would be 13.50. But we really need out of this is the H2. And that the H2 is going to be 2,393.2. We might also find HF. And you're going to go, why do we need HF? Well, just trust me. You need HF of 191.81. And so, using this equation up here, we first note that they didn't say anything, or at least I didn't read anything. Let me see if they being me. A steam has a mass flow right here. So what you have to do, what you have to assume from this is the thing is well insulated. Probably should have said well insulated, so that no heat is escaping the surface of the thing. So what we end up finding is we have this power, I should say, that's going between 1 and 2 is going to be equal to the inlet. It's the same, these are the same mass flows, so we don't need to make the distinction. And that's going to be H1, but this is going to be the total right in there. So we note that this H tot right there is, or the H tot right here is listed, I have it down here under entropy. So it's, we can ignore the GZ, but it's going to be 1/2 V1 squared. So plus 1/2 V1 squared minus this other part right here, m dot be H2 plus 1/2 V2 squared. So putting all those things in there, and this is said that we had 12 kilograms per second. I'm not going to write out all of these things right here, but I will point out to you in them, right, that this has a difference between H1 and H2 of 978 kilojoules per kilogram compared to a difference in the velocities of 1.95, right? So this is less than it's like 0.2% of the of them right there. So it doesn't the velocities are often ignored, right? It just doesn't matter all that much. And you know, the smaller of the two is even more so extra small. So what we end up here is 11,759 kilowatts. Oh, I just thought of something. Oh, that'll be good. No. Yes. Just a second. Okay, so that would be the answer to part A. Yay, we got 11,700. But now we want to condense all the way. Now we're not going to subcool it, which actually does happen. Tell you the truth, we're not going to subcool the condenser, the condensate, but we're going to get rid of all the rest of it. Right now is 92% steam inside the condenser, right here. Like as it's coming out of this thing, it has gotten to this point, and now the condenser is going to get rid of all the other latent heat of vaporization. Going to dump it into the ocean. So we are in essence we're going to have the same pressure all the way. We're going to have the same temperature right here. So the outlet temperature that we had right here, and this should have been this Tsat right here. This temperature, that Tsat that we would have had would have been 45.81 degrees Celsius. That's what we're going to have about the heat exchanger. So we're going to go between, what we're saying is we're going to use the same law, the first law here, but it's going to be contained inside a condenser, right? So we have in and out, but we're also going to have in and out. And so now we've drawn a control volume around this, and mass flow is coming in here, mass flow is coming out here. Mass flow is coming in here, mass flow is coming out there. So what we've essentially used, we're using that same equation right here. Summation m dot h, and these are ins minus summation m dot, these are h out. But we're going to say, well, this thing is insulated enough and it doesn't do any work. So what we're basically saying is, and I got to give this, I got to give these guys names right here. I don't know what to call them. So this is 2 and 3, and I'm thinking this is, I'm just going to go A and B. I don't know what, I just didn't want to give it other numbers. And then I'm going to go crazy with my subscripts. So what we're saying over here in this is, let's bring them out right here. So we're going to go m summation dot is going to be equal to summation m. These are e's, I guess it's supposed to be e's. This is a powerful equation right here. This right here, I mean, just in terms of just, I don't know how many different ways that you could use this same thing over and over again, but in terms of balancing out energy, that gets used a lot. And what you can, now we could say, we could go M, so these are the ins, so you have M2H2 plus MAHA, and I shouldn't, yeah, I guess I'll call that here, all right? So, but then on coming out of the thing, this is, I'm not going to call that m dot 3 because it's the same one, conservation of mass. So I'll call it 2. It's the same n dot here as it is right there, right? That m dot and that m dot are the same. So this is H3 because it did change entropies here. And then this is going to be plus m, now it's the same as MA because that's the same mass. And then we go HB. And then arrange them over to the other side. So it's going to be m dot 2 H2 minus H3. And then it's going to be equal to m dot A H. I don't want to say this. I'm going to do this wrong. I'm going to do this wrong. I think I'm okay. Yes, okay, because this would be, all right, so, but this is water all the time. So you just have to use m dot A times CP, and then this is going to be, I'm just going to call it delta T. This is the delta T, and that's the 10 degrees, right, that I talked about in the beginning. We don't want to hurt the fish. So we want to find out what MA is. And over here, yes, sir.
Could you re-explain how you broke that up in the last step?
Okay, so we started with this equation. Is that good?
Yep, that's fine.
Okay. These two are crossed out because there's not really any heat exchange coming out off the thing. I mean, it's nominal and it doesn't really matter. So, but it's not enough that anybody cares on a condenser. So we just treat it like it's 0.
Okay.
And there's no work going on because there's no work crossing the boundary in any way. So now we have summation of everything coming in minus the summation of everything coming out. When it comes about flow, and we will introduce this idea in fluid mechanics called the Reynolds transport theorem, which is just a big fancy word of saying mass also often carries stuff with it. In this case, it carries heat with it. And by way, so we're only looking for things that are crossing the boundary that have mass flow as part of them. And we're taking a look at their enthalpy, right? So that guy right there gets broken down to coming in and then going out. And so I said, well, as we're calling it here, 2 is coming in, and also A is coming in, so they go on the left-hand side. On the right-hand side, we have 3 coming out, and I didn't bother to call it M3 because M3 is equal to M2. It's the same mass, right? These things don't mix up, even though I didn't show them, you know, little tubes and stuff coming in through there. If it comes in 2, it has to come out 3. It's not a mixing thing. We don't want the seawater to mix with our condensate. And then the same thing true with here. You know, I just went ahead and used MA here because it's the same guy coming in that way as it coming in as out. But here's B. And then A and B are equal to each other.
I was saying is H3 the same as H2 as well?
H3 is not. H3 is right here. Right? Because this one changes from H at 2 and H at 3. Okay. Yeah. And H2 right now for us is going to be this guy right here. And H3 now is going to be this guy right here. We'll need to why? Because the condenser removes all of the steam out of the steam. It's like now it's completely water. So here is the HF from the thing coming out. I think I could just rewrite that.
And we're solving for MA in this case?
Yes, exactly. And we're going to be able to, we should be able to look it up, or we'll pretend we're in the Great Lakes, and we'll just use water instead, fresh water instead, because I took a ship all the way from the entrance to the St. Lawrence Seaway all the way up to Duluth. Went through all those locks. It was neat. So I'm gonna see if they do have seawater. That should be table A4. They have water, but they don't have seawater. Anyway.
So we're using the constant or specific heat of water in this case?
Yep, yep. So for this, if we put in the mass flow that we were given in the beginning, which was 12 kilograms per second, and H2, which was the partially condensed steam, right? It was at 92% quality. And now we'll have the complete, at that same temperature and pressure, but now we'll have only water, and then we have, this is M dot A that we're looking for. This is CP is given in table A4 as water somewhere. Water 4.18. And then the temperature difference, we were told we were trying to keep was 10 degrees. We only want a rise of 10 degrees. So this ends up being a lot. The pumps on board a ship have, for the seawater, but interestingly enough, on some ships, to try to save some amount of money, it's not a lot, so they could, not saving money, saving fuel, they'll turn off those pumps, and there actually is a scoop, and they bring water in from the ship. It's underneath, you can't see it. I wasn't on one of those ships. All right, so the mass flow of the A, which is I might call salt water, or now it's fresh water because must be in the St. Lawrence Seaway, the Great Lakes.
Wait, how do we get delta T?
It was a given. I'm making up this problem, but I was explaining to you that it is an important thing here to keep the you don't want to make it too hot. I mean, it quickly dissipates, but it's actually more of a problem on land-based power plants that use seawater. They're right on the shoreline, and they take seawater in, and they push seawater out. There's actually a problem in the book that describes that scenario, and what you would try to do to reduce that or diminish that amount of thermal pollution, they like to call it. All right. I wish I had more time to be more organized to give you a better preparation for the thing. I will say that just doing more problems and figuring out what you did wrong on previous homework problems, and then trying to find other problems like that. Also, the example problems that I did, like not all of them were great, but some of them were. I picked them from other books so that you had a lot more to choose from, and just the more problems that you try to do on your own without looking at the solution to the thing, taking it from a blank page and trying to challenge yourself, and then comparing the results once you get finished all the way through and seeing, hey, okay, I got that one right, great. I screwed that one up. Oh man, I need to do another one, and then do another one. Until you start getting them right all the time. All right, thank you for your patience, as my brain isn't working correctly. But that was the one I was talking about. They were talking about thermal pollution. What's that? And the recording now.